Okay, so thank you so much for this opportunity to have this presentation here. I introduce myself. My name is Jesús Alberto Getial Barragán, and we have developed this particular research with Silvio, Ricardo, Timarán, Pereira. We are part of University of Nariño in Pasto, Colombia. We are part of the research group in research applied to systems. And well, for now, I'm going to talk about this research that we developed about effort estimation in software development projects using supervised machine learning, a comparative analysis with ISBSG data. So let's start. What happened? Okay, so the 6 points that I prepared for you are the following that we can see here. First, I'm going to talk and give a brief introduction about effort estimation, importance and challenges that we have on this. And after that, the application of the main methodology that we have for data mining and machine learning projects, that is CRISP-DM, to the repository that we have. The third topic is to talk about the machine learning models applied, the results and the evaluation that we had. The fourth topic will be the highlighted models. We found that the decision tree and the random forest were the best options for this particular data set. And the decision tree was more optimal in order to acquire the patterns. And the other one is more stable, and it has a better prediction accuracy, I can say. So we will talk about that after that in the results. And after that, to the end, I will talk about the conclusions and the future work. So let's start. As the first point, we have what is the effort estimation? What is the importance and the challenges? So in my case, I've been working as a software developer over 7 years, working with many technologies as full stack developer. So I've been involved in the industry of the software, and I know that it's really important, the software estimation, to know very well what is the size of the software, and based on that, compute what will be the cost, how many people will be involved in the construction of the particular software, and well, time that will be required and everything that will be involved. So it's highly important as a first approach to have an estimation, and of course to have of the size, and of course to have the estimation of the effort. I mean, how many hours will be involved in that. But that depends of many factors. That's why this particular thing it's a little bit complex, I can say, as a first approach, but in fact it's complex because we have software for many things. The heterogeneity and the intricacy of functional and non-functional requirements, it's where, I mean, for example, we can do software for whatever we can imagine. We can make software for games, for hospitals, for accounting, for commerce, etc. So we have a lot of heterogeneity, and the people who works on this is are involved to many factors, like the expertise, the motivation, and we can consider here too the emotional states while developing. So it's really hard to have like a standard of how we can estimate this particular thing. So that's why the ISBSG data is highly important, and the challenge here is high. So as it is really important in software development, we have during the history, I can say, we found several approaches. So non-algorithmic, algorithmic, heuristic, well, this composition. For example, the non-algorithmic, in here we can, in this classification, we can find the planning poker. The planning poker is the most used method that we can find in the industry, where we have a user story, a particular piece of the software, and several experts in that particular development piece will point how many efforts will be involved in a particular user story, And after that, based on the Fibonacci series, we define what's going to happen and what is the time that will be involved on that. But that depends, as I mentioned, of the expertise, how is the people, what they want. So it's not something that has much accuracy. The other estimation techniques that we have that are more has been more used, I can say, to estimate the size. For example, the functional adjusted function points that help us to have a better estimation of how big is our software that we want to build. And the others that are the heuristic. We have two approaches, the supervised and unsupervised. So for this particular research, we take care about the supervised learning. So in this case, we use the existing data in order to see how we can use it to predict at the end the effort, the software effort estimation in hours that will be involved to complete a particular software project. So in that case, so as we know, the CRISDN in the right part of the screen, you can see the CRISDN methodology. Here we have as a first step the business understanding. We need to understand what is in this case is the software development, what is involved, the things that I talked before in the other slide. And now I'm gonna give a brief description about the data that we are gonna consider here. That is the ISBSG data. So as you can see here, I took only 2 pictures of the demographic document that is delivered in the release of the data set. And here we have projects of several sizes, as you can see in the first project, and that handles different methodologies too. So this particular data set, it's pretty good because we have the effort already measured, I can say, of existing and already developed projects, so we can know how they were implemented, how many people was involved, the expertise of those people, the language that they were using, several characteristics and parameters that we have. For this particular release and research, we use the 2022 release that contains 255 parameters, and the number of records is 11,281. So, as you know, for the machine learning models, we cannot deliver all directly the data set. We need first to pre-process, compute a subset of this total data set in order to have a similar data and that we can compare and have a good input to our model. So that's the other part that we will check here, that is the data preparation. So for the data preparation that we have here, we applied 3 main steps. So the first one is the apply filter. What is the filter? The information that we find in the left side is the filter that we apply to the data. So we can see that we selected from all the database only projects that belongs to the development platforms of PC, Multiv, and MF. In project score, as suggested by the guideline of the use of this particular data set, we use the pointing score A and B. The normalization rate between the values that you can see there, and the count approach, we wanted only to use I4+, but we try to, because there are no many registers of NESMA, only to add a brief variability there and try to play with this. We added those registers from NESMA that with this count approach, but only to add a particular variability to our research. Because you know they are based on the same function points, but well, they differ in how they do, but as they are based in the same size approach, I can say, so that's why we consider it in the same subset, and we exclude all the rows or the registers, I can say, that were computed with lines of codes. The second one in the data preparation is to check the correlation that we have in the parameters. So this is for the numerical parameters. So as you can see in the first picture that is in the left side, so we can find several parameters that are correlated with others. So the information is the same, and we remove those parameters too. And all the parameters that are over the 0.84 in this correlation, we removed them, and we have the correlation matrix, as you can see there in the other picture that is below, that we have a clean numerical parameter subset, I can say here. The other data preparation step is to remove all those fields, all those parameters that contains more than 30% of nulls, because in the documentation, the state of art suggests that it's not correct to add a lot of synthetic data. So for that reason, the limit, the top limit is the 30% for that. So that's why all the others were removed. And for those that are below the 30% of null values, were available, I can say, or were good in order to apply a synthetic data preparation. So how we did? For those that are categorical parameters, we use, for those that contains that the pictures that you can see there tell us in blue how many values, how was the percentage for the particular parameter of null values and non-null values. The same for the numerical parameters. So for categorical parameters, those that are below the 10%, we replace with synthetic data using the mode. And for the others that are between the 10% and the 30%, we applied a quick C4.5, that is a decision tree algorithm, in order to predict what will be the values that should be in those chains of data, I can say. And for the numerical data, in a similar way, for those that are below the 10%, we apply the synthetic data with the average. And for those that are between the 10 and 30, we apply the median. With this, we have a preprocessed data, but it's still pending only one step, that is the outliers. So after all of that preprocessing, we have the picture that we have in the left side. So as we can see here, we have several values that are outliers in this box plot. So we applied the third method that we can, the three methods that we can see in this picture, the winsorization, IQR, and z-score, in order to pass through all of this process and fix these particular outliers that we have in the left picture. The final result is the data, the subset, as we can see in the right side. So without outliers, that is better prepared in order to be input of machine learning models. So as you can see here, in the right side, we can find the histogram of our data. We have a balanced subset, and as the guidelines of ISBSG data tell us that all of this data is prepared for statistical analysis, we applied this statistical analysis to consider 4 categories of effort. And our object variable is the summary work effort that consider the hours that will be involved in develop and complete a software project. So the 4 categories are those that we defined: very low effort, that are below 500 hours, moderate effort that is between 500 hours and 1050 hours, the high effort, the values that you can see there, and very high effort. With these 4 categories, we can start to apply the machine learning model, that is the information that we can find at the below. With the preprocessed subset, we have the proper input for our machine learning models. And what are the machine learning models that we evaluated? In the CRISP-DM methodology that we see in the right side, after the data preparation, we have the modeling stage. So the state of art show us that these are the most common the most common machine learning models that have been used for this particular data set. So we try to check and verify how is this behavior. So we tried with AdaBoost, decision trees, random forests, support vector machines, multi-layer perceptrons, logistic regression, canaries, naive biased, and all of them were optimized in order to have a standard for all of them. All of them were optimized with a grid search combined with stratified cross-validation, and we use a partition of 80 for training and 20% for testing. So the selection of the hyperparameters for each one of them in order to have a standard was the accuracy metric. So the results that we have after the application of the pre-processed subset that I showed you to all of these machine learning approaches that were implemented in Python is the following. So these pictures are the median square error versus, well, the iteration, dips, number of trees, that depends of the algorithm. So as we can see, this is the behavior for some of them, because here we can see the training and the test plots for each one of them. So some of them have one overfit, I can say, because the test has a higher error stabilization in comparison with the results that we have with the training that has a better approach, right? But in general, here, considering this, we found this is like only to have like a graphical, I can say, visualization of the results. But considering these particular metrics, we can define and check better what are the best approaches to this particular data set. So considering the accuracy, F1 score, the MCC, Gini, and AUC, we have that the decision tree and the random forest have the best results for each one of them. So they are highlighted in green. As you can see, those are the results. As you can see here, the random forest is the best one, but the decision tree led us to understand better the patterns. We can read better how the tree is implemented step by step, and we can check each one of the branches and verify what's going on and see what are the main parameters that take us for a particular category. I can say for the category 1, we have that this and this particular parameter is most important, and for each one of the categories we can check that. So that's why we choose the two approaches, and we can have the random forest as the best for prediction in our subset, I can say, and the decision trees in order to reveal patterns. What we did in order to understand better what about the generalization, robustness, and stability, we performed several cases. Considering the subset as our 100%, we divided this one in 3 subsets, I can say, for validation: 10%, 20%, 30%. And for each one of them, for the validation, we split another subset in order to perform the training and tests that is the part of all the process to build the machine learning model, I can say, to develop this. And validate with totally unknown data, that is the validation data that is considered here. So we have several combinations here, and it's interesting that for both methods, the best combination was the 10% for validation and 20% for the test. So the results that we have, the first one for the decision tree, that is that belongs us to have a pattern recognition. The results that we have in the picture that is on the right show us what was the behavior for the training in blue, for the test in orange, and for the validation in green. We see that for is totally unknown, we have like a higher error. But well, so the categories, we found that this particular information that we find here, are the main parameters that mark the difference, I can say, for each one of the categories. For example, and we found that the high productivity and not specify industry sector increase the time in the delivery of the software project, and that could be related to the pressure that is posted to the developers in order to deliver, and not specify a particular and only one piece of software. Be involved in many things at time that is generating an increase in the time of the delivery of the software. Well, and related to the random forest, we found that for different combinations, I posted here the different pictures of different combinations. We saw that this is a very good approach that with different percentage of training and validations and tests is able to acquire the patterns of the data and is not so much affected with these kind of changes. So it's a very good approach in order to be applied in the industry, I can say. So, well, as the conclusion, we have that the highest performance was for the random forest. Well, Adabus multi-layer percentron exhibited significant overfitting tendencies. So in the industrial context could be not good, but I think that for the multi-layer percentron we can explore more and more combinations. Support vector machines and the other that I referred that had a very low accuracy, so they are not good for industry approaches too. And well, here patterns associated with higher effort categories predominantly correlate with industry sector risk and development teams' work pace. Well, pattern recognition analysis highlighted software size, development team productivity, the chosen development platform, and the programming language as the key determinants for classifying projects into the established effort categories. Well, the future work that we have is purpose is well to check, because as this was developed, this research was developed with the version of 2022, we can have a better approach. It could be interesting to check the latest approach of the latest release, of the ISBSG data. Check another ensemble configurations in these machine learning models, and we can improve the hyperparameter optimization techniques. We can choose a particular one and explore different things to synchronize these hyperparameters, because in this research we handle only one standard for all of them because it was a comparison. And well, of course, apply this random forest to a particular industry model, and could be this particular one be added in project management tools such as Azure DevOps and Jira. So, well, that is the research that we wanted to share with you. Thank you so much for all your time, and well, I'm here ready for your questions. Thank you.
Oh, thank you very much. Yeah, you mentioned comparing your data with the latest ISBSG data, and I think we'll have another release out within a couple of months. So looking forward to that. We have a question from Srinivasa. You've done extensive analysis in your ML models. could you compare predicted values from these models with actual values of effort or schedule or defect density, as the case may be?
Oh, sorry. Could you please repeat the question? I lost the...
That's okay. Could you compare the predicted values from these models with actual values of effort or schedule or defect density, as the case may be? Srinivasa, you open your mic if you want to clarify anything.
It's because sorry, I cannot. You have, oh, I can see here the question.
Okay,
To
good.
compare predicted values from these models with... Okay, got it. Yeah, thank you so much for your questions. So it's interesting, the question, because for this particular one, in the filter, we only considered the project registers, I can say. So we didn't consider those that belongs to support projects, or those that are related to issues, only implement work to solve issues. That is related to the defect density. So in this particular case, we only consider data that is about a full development stage, I can say. So considering planning, considering development, considering testing. So we can compare the results of this evaluation and predicted values with only projects that are totally completed too, because the base of the project of the data that we filtered is only for projects that were totally completed, not for... I know that ISBSG Data has registers for support, for densities, issues, and those kind of things. So in this particular case, it was only focused for projects and not for support cases, I can say. So in this case, we cannot compare these particular values because are different. I can suggest that we can consider the other database that is for the support and defect densities, and have results and another trained model for them, and then we can compare those values.
Okay, thank you.
Thank you so much.
Okay, I don't think we have any more questions.